ഹലോ ഗുഡ് മോർണിംഗ്. നമ്മുടെ മെക്കാനിക്സ് ലെക്ചർ 4-ൻ്റെ പാർട്ട് ബി ആണ് ഇവിടെ ഡിസ്കസ് ചെയ്യുന്നത്. സോ ഹിയർ വി ആർ ഡിസ്കസിങ് ദ എഫക്ട്സ് ഓഫ് കോറിയോലിസ് ഫോഴ്സ്. വി നോ the expression for Coriolis force is Fc is equal to minus 2m into omega cross velocity in the rotating frame. So if we have two frames S and another frame S dash, and S dash is rotating with some angular velocity omega with respect to S, and with respect to F dash, suppose a particle is having a velocity v rotational, then in the rotating frame of reference, the person sitting in the rotating frame of reference will feel that some force is acting on this particle, and that force is called the Coriolis force, and the expression is omega cross v rotational into minus 2m. Now we know that omega cross v is simply magnitude of omega cross v is omega v into sin phi, where phi is the angle between omega and v. When phi is equal to 0, that means omega and v are having the same direction, or omega that means omega is parallel to velocity in the rotating frame. The fictitious force that is the Coriolis force will be equal to 0. Now if phi is equal to 90 degree, omega and v rotational are perpendicular to each other, so the Coriolis force will have a maximum value because sin 90 is equal to 1. That is the maximum value of sin. Okay, this much things we have discussed in the previous sessions, I think. Now let us see what is the effect of a moving object on the surface of the earth. So here we are restricting our discussion on the horizontal motion of objects on the surface of the earth. So in another class we can discuss the effects of Coriolis force on a vertically falling body. Now we can consider three different positions on the surface of the earth here. So this is the north pole of the earth, this is the south pole, and this is the equatorial plane. Now at the north pole, angular velocity is directed vertically upwards. Earth is rotating in this direction, anti-clockwise direction. Now a person is standing here in the north pole, so we can take that position as location 1. Here we have another person standing on the equatorial plane. So this is the plane, equatorial plane. So the person is standing here, and that location we can take it as 2. And another person in the south pole, his top side is this, and you can see that the angular velocity is directed towards the surface like this, and we can take this as location 3. Now let us consider first the location 1. Say this is the surface of this particular person standing on the north pole. Angular velocity is in the vertically upward direction. Now in this case, suppose a particle is moving in this direction, in a horizontal direction, horizontal motion of a particle. The Coriolis force will be opposite to omega cross v. We know omega cross v will be in this direction. So if we rotate a right-handed screw from omega to v, so this way, so this direction will be the direction of omega cross v. So Coriolis force will be acting in the opposite direction, because Coriolis force is minus 2m into omega cross v. So it will experience a Coriolis force in the opposite direction. That means the Coriolis force acting on the particle will be in this direction. Now What is the effect of Coriolis force on the motion of this particle? When the particle moves in the north pole horizontally, it will experience a force towards the right of its motion, right of its path. As a result, the path of the particle may be get deflected. Suppose the particle comes to this position, the direction is changed to this position. So in this case also, V is in this direction, omega is in this direction, omega cross V is perpendicular to both, minus omega cross will be opposite to this. That means particle will again experience a force in this direction. So continuously the particle will experience a force towards the right of its path, and as a result the straight line motion of the particle may end up into a circular motion like this. In the absence of other horizontal forces, the particle will undergo a circular motion in the clockwise direction in the northern hemisphere. So you have to remember one thing, that in the absence of other horizontal forces, because Coriolis force is a very weak force. If some other forces are acting on there, that force may be predominant, so the effects may be different. Now let us consider the position 3. What is that? Effect of Coriolis force on the motion of a horizontally moving particle at the point 3 in the south pole. So at the south pole you can see that the angular velocity is directed towards the surface. So say this is the condition we can take. This is the plane. We are considering a plane in the southern hemisphere. Here angular velocity is vertically downwards towards the surface. Now suppose a particle is moving in this direction. So if you rotate a right-handed screw from omega to V, omega is in this direction, V is in this direction. What is omega cross V? This way when you rotate, omega cross V will be in this direction. Then the particle will experience a Coriolis force opposite to the direction of omega cross V. So that will be in this direction. That means a horizontally moving particle in the south pole will experience a Coriolis force to the left of its path. If no other horizontal forces are acting, the straight line motion of the particle will end up into a circular motion in the anti-clockwise direction. So this you can see, these things are discussed in example 8.9, the motion on a rotating earth, in the example 8.9 of the textbook by Klepner and Kolamko. Now and also it is discussed in the last paragraph of that particular example. Anyway, you have to remember that in the northern hemisphere a horizontally moving particle will experience the Coriolis force towards the right of its path, and the southern hemisphere it will experience the Coriolis force to the left of its path. Okay, one more thing I forgot to mention. I have to mention. So that is at the position 2. So we are discussing only the horizontally moving particles. Here angular velocity in this direction, omega is in this direction, and suppose the particle is moving towards the north or towards the south, omega and V are in the same direction, so omega cross V will be 0. On the other hand, if the particle may move in the like this is the direction of omega, say the particle may move towards the, say this is north, this is east and this is west, may move towards the east or west. When it is moving towards the east, omega is perpendicular to the velocity. So omega cross v will be in the downward direction. So minus omega cross v will be in the upward direction. So the Coriolis force will be in the upward direction. So when it is moving towards the west, omega cross v is in the upward direction. So minus omega cross v will be in the downward direction. So it will result in it will experience some upward or downward force due to this Coriolis force. But we can see that there is a strong force is acting in the downwards, that is the gravitational force. So comparing to this gravitational force, the effect of Coriolis force is very, very negligible. So we will not get any noticeable effects of this Coriolis force when the particle is moving either towards the east or towards the west. So the horizontal deflection happens when the particle moves in horizontally on the surface of the earth. It will not experience any horizontal deflection in the equatorial plane. In the north pole, it will experience a force towards the right of its path, and the left southern hemisphere, the south pole, it will experience a force towards the towards the left of its path. Now let us consider a point in between the poles and the equator. Let P be this particular point. Now this is that equatorial plane. Now we can draw a line from the center of the earth to this particular point. If lambda is the angle made between this line and the equatorial plane, that angle is called the latitude of that particular point. So you are familiar with the term latitude. Now we can extend this line like this. If this angle is lambda, what about this angle between this and this? This angle and this angle between this is 90 degrees. So if this angle is 90 lambda, this is 90 minus lambda. Now at this point also, the direction of angular velocity is same. Direction of angular velocity is this, so angular velocity direction will be this. Now angle between omega and this line, this radial vector, this angle is 90 minus lambda, so this angle also will be 90 minus lambda. So if we draw a surface parallel to the Earth's surface at this particular point, or if we draw a tangent at this particular point P, the angle between this tangent and the angular velocity will be, the tangent and this normal will be 90 degree. Angular velocity and this normal is 90 minus lambda. So angle between this tangent and angular velocity will be lambda. So we can split this lambda into two components, one parallel to the surface and one perpendicular to the surface. So if this angle is lambda, this horizontal component of angular velocity is omega h is equal to omega cos lambda, and the vertical component of omega is omega sin lambda. Now let us see the effect of this Coriolis force on a horizontally moving particle at this particular point P. Now on a horizontally moving particle, Fc is equal to, the Coriolis force is equal to minus 2m into omega cross v. But we can split this omega into omega h plus omega v. These are vectors. That is minus 2m into omega h cross v minus 2m into omega v cross v. Now let us see what is the effect of this omega h cross v term. So at this surface, omega h is directed in this direction. So this is the direction of omega h. So we can draw that plane here. So omega h is in this direction. Now suppose the particle is moving directed towards the north like this. V is the velocity of the particle that is parallel to omega h. So what is the effect of omega h cross V? There are parallel direction. Sine 0 is the angle between omega h and V. So this is omega h in V term reduces to 0. On the other hand, if the particle is moving in the opposite direction, these are parallel directions. Again, omega h cross V is equal to 0. Now, if the particle moves in this direction, omega h cross V, so it is in the downward direction. So minus omega h cross V will be in the upward direction. That means the Coriolis force will be acting in the upward direction. On the other hand, if the particle is moving in this direction, omega h cross V is in the upward direction, minus omega h cross V is the direction of Coriolis force, that is in the downward direction. So no horizontal displacement can be produced by this term. This term can produce the effect of this term is some vertically upward force or downward force depending on the motion of the particle towards the east or west. So if this is the north, this direction is the east and this is the west. Say this is the south. So this Coriolis force is negligibly small compared to the gravitational force. So not much effect, no effect can be observed due to these vertical forces. Now let us consider this term omega V cross V, the vertical component of angular velocity. Now here the angular velocity is in the upward direction, that is in the vertically upward direction. Now so that is, this is the plane, so angular velocity is in the vertically upward, that is vertical component of angular velocity is in this direction, in the direction of this radial vector. Now suppose a particle moves like this, horizontal direction. You can see that effect is same as that we have found here when a particle moves in the north pole. So omega is perpendicular to the surface. Here omega V is perpendicular to the surface. So the magnitude of omega cross V will be different at the poles and at this plane, but the effect will be the same. Here also the particle will experience a Coriolis force towards the right of its path, continuously towards the right of its path. So at any point on the northern hemisphere, a horizontally moving particle will experience a Coriolis force towards the right of its path. So that is the point. Now let us see what will happen at some point here in the southern hemisphere. Some point in southern hemisphere. Now, so this is the say this is the Earth and this is the angular axis. Angular velocity is omega in this direction. So at the southern hemisphere, omega is in this direction. Now if we consider some point here, P, the angle made by this line from the equatorial plane is, so you can take this line, this is the line, you can draw a line from the center of the earth to this particular point. If this angle is say lambda is this angle, so this angle will be 90 minus lambda, this line, and this axis of rotation of the earth is 90 minus lambda. Now at this point P, the direction of angular velocity is parallel to this. So this is the direction of angular velocity. Omega, direction of omega is this. But you can see that it is directed towards this surface towards the surface at this point. Now if this angle is 90 minus lambda, this angle also will be 90 minus lambda. Here also we can draw a tangent at the point P. So we can imagine a horizontal plane here, a plane horizontal to the surface of the earth at this particular point. Now if this angle is 90 minus lambda, what about this angle? Is lambda. So this this angle also will be lambda. Omega is in this direction. So we can split this omega into two components, one horizontal to the surface and one vertical to the surface. The horizontal component is omega h into cos lambda, and this component is omega h is equal to omega into cos lambda. This component is omega v, that is equal to omega sin lambda. But you can see that omega sin lambda at the point V is directed towards the surface. Now the effect of this omega h is same as that we have discussed in the case of some point in the northern hemisphere. So this effect is Coriolis force will when it is parallel to omega h. So when the particle moves in this direction or in the opposite direction, the Coriolis force will be 0. When it is moving in a perpendicular direction like this towards the east or west, so Coriolis force will produce the effect of Coriolis, direction of Coriolis force will be either upwards or downwards. So it will not produce any noticeable effect. Now let us see what is the case. What is the effect produced by this term omega v, the vertical component of angular velocity. Now at the point, this point P in the northern hemisphere, angular velocity is vertically downwards. So if a particle moves here, omega cross v, when you turn a right-handed screw from omega, the direction of omega to direction of v, in this direction, angular velocity will omega cross v will be in this direction. So Coriolis force is minus omega cross will be in this direction. So the particle will experience a force towards the left of its path. Same thing we have observed in the south pole. Okay, same thing we have observed in the south. So for any point in the southern hemisphere, a horizontally moving particle will experience a Coriolis force which tilts the changes the direction of the particle towards the left of its path, and as a result the particle may go up to a circular path in the anti-clockwise direction in the absence of other forces, same as that we have observed in the case of south pole. Now at any point in the southern hemisphere, horizontally moving particle will experience a force towards the south of its path. You can see that. So this is the earth, this is the equator, this is the north pole, and this is the south pole, and this is a line drawn on the surface of the earth connecting the north pole and the south pole. Suppose we have a particle moving from the equator to the north pole. In the northern hemisphere, the particle will experience, it is moving in this direction, so you can see that the particle will experience a force towards the right of its path. When the particle is moving from the south pole to the equator, the force acting on the particle will be in the opposite direction. It will be get reflected to the left of its path. On the other hand, again, if the particle is moving from the north pole to the equator like this, again the particle will experience a force towards the right of its path. What is the right? This is the right side. Now, if the particle is moving from here to the south pole like this, it will experience a force towards the left. So what is the effect of this particular force on this movement of this particle? The particle, in the absence of other horizontal forces, the particle may end up into a circular motion like this. The motion of the particle may end up into a circular motion like this. That is in the clockwise direction. And what about this motion? So this motion also tilts the particle like this, and this also may end up into a circular motion in the clockwise direction. Now what about the southern hemisphere? Here So the particle is moving in this direction, so it will experience a force in this direction. Okay, so the particle may move in this direction, so there is some anti-clockwise motion. Here the particle, when moving in this direction, it will experience a force, so the direction of particle may change and it will end up into a motion like this, again in the anti-clockwise direction. So you can see that this anti-clockwise and clockwise motions in the northern hemisphere happens only in the absence of other horizontal forces. In the presence of other horizontal forces, the direction of rotation may be different. Anyway, one thing you can conclude that in the northern hemisphere, a horizontally moving particle will experience a Coriolis force towards the right of its path. In the southern hemisphere, on the other hand, a horizontally moving particle will experience a Coriolis force towards the left of its path.